Alright, welcome back everybody to another video of numerical methods online. Today we're going to be talking about computer project 5 nonlinear equations using nonlinear Newton-Raphson. Right now I'm inside of the assignment tabs. I'm actually looking at computer project 5 right now, and these are the files that you're going to be provided. You're going to be provided the PDF file for the project with all the instructions and expectations. You're going to be provided a Newton-Raphson.m file. This is the main script. This will be the file that you'll be running. You're going to be provided the f nonlinear.m. This is actually a function file. Same thing with the Jacobian. These two files, we will modify them, we will add content to them. However, as I mentioned during my lab sections, you do not run the function files. The main script is the only file that you will be running. However, you do require to download all three of them, so go ahead and download them. And in my case, I downloaded all the files and I put them right on my desktop. See, there they are. Those are the three files and the PDF file. So I will go ahead and open the PDF file and go over it. For project 5, here are all the instructions and all the expectations. As I mentioned before, same thing as the previous projects. In this project, we're going to be looking at the heat transfer of a bar. We have the equation of heat transfer for the 4 internal nodes, so we have 5 nodes in total, and the temperature at the base and the temperature at the tip, like the temperature at each of the extremes, they're given. Those represent our boundary conditions, and these functions, each of them represents the different nodes. So this will be the input function for our nonlinear file, and if you read through it, you will find all the explanation, all the details about how this process works and what they want us to do. But in short, we're gonna write these 4 equations into our f nonlinear file. We will use these constant values inside of that same f nonlinear file. We will modify the calculation of the Jacobian, which will use first order backward finite difference to approximate using a step size delta x of 10 to the negative 5. This I will show you where to input it. And for our initial guess for the nonlinear Newton-Raphson, because we're talking about 4 equations, we will require to have 4 initial guesses. So we have an initial guess vector, and that's what we're going to use in our code. So they also want us to show the initial elements of the Jacobian, the temperatures, T for I is equal to 1, 2, 3, and 4. So the temperature at the 4 different nodes that we're talking about, and then the initial residual. For the second part, we will repeat this same exact process. However, we will find the linear coefficient k0 by setting a equals to 0. So this sort of linearizes the problem, makes it behave as in a different manner. So let's get to it. What I'm gonna do is I believe I have Octave open right here, and this should be what you look at as soon as you open Octave. In my case, I put my files. I have my files on the desktop, so there they are. So what I'm gonna do is I'm gonna go within Octave. I will use this file browser feature on the left, and I will go to my desktop. I will open Octave, and then I'm gonna go ahead and open all 3 of my files. There you go. So those are my files. I need a little bit of room, so I'm gonna move this to the side. And one of the cool features about Octave, if this is too small like it is right now, I can actually hold down Control and press the plus key or the addition key, whatever you want to call it, and I can make this bigger. So hopefully you're able to see it better. But these are gonna be all my files. I'm gonna do the same with this, and I'm gonna do the same with this one. And what I'm gonna do next, since I'm gonna grab this and just put it on the side. There you go. So okay, the first step is I'm gonna go into my f nonlinear, and you can see here that I'm actually given 2 of them already. They're not the same exact function. This is an example. So but what I'm gonna do is I'm gonna take this 2 and I'm gonna copy them, and because here we're talking about 4 functions, I'm gonna have my I is equal to 1, I is equal to 2, I is equal to 3. and I is equal to 4. And I am going to replace this function, which it will actually take me a while to type it because I want to make sure that I type it correctly. I will replace it with this function. Now, wherever you see a T1, T2, or anything like that, that represents the variable inside of the vector. So this x11 from our initial guess vector, each of those values, that means that value gets plugged into that part. This is an array, so x11 represents the first value, x21 represents the second value, x31, because remember we're solving for the temperature at each of those nodes, and that is what is known as the solution vector. So when we're talking about T1, T2, T3, keep in mind they're all components of an array called the T array, the solution vector. Um, for the sake of simplicity and just because it's already given as x's, I will keep it as x. However, you're more than welcome to use whatever you want instead of x. Just keep in mind that if you do desire to you decide to change it to something other than x, you have to make sure that that change is reflecting here in the input of this function. So I'm gonna leave it as x, and I'm gonna go ahead and start typing this. So this will be k naught plus, let's see, plus a divided by 2, and this is probably gonna take me a while. Instead of writing x1 comma 1, I'm actually gonna, since this is a one-dimensional array because it's a vector, I can actually go ahead and just write x in x parentheses 1 instead of having to write x11. They actually mean the same thing, but it represents less typing, which I really like. And I'm gonna call this one t naught. I'm gonna go ahead and close this. This will be multiplied by t naught. I should probably make this smaller so it can be seen. Then minus 2 times k naught plus a divided by 2. Really hoping I don't make a mistake. T naught plus 2 times x1 plus x2. Close that one, and this multiplies times x1, and then plus k naught plus a divided by 2 multiply times x1 plus x2, close that, and all of that multiplies by x2. So that will be, let's see, I guess I can make it smaller so you guys can see it. That will be my equation for the first one, and what I'm gonna do is I'm gonna highlight it like so. Oh, there you go. And I am going to paste it here and here and here. This is, I believe this is the fastest way of doing this. And what I'm gonna do is I'm gonna go over it and just make sure that all the things that I need to change, I do actually change them. So this becomes that, this becomes x1, then this becomes 1, 2k, a divided by 2. This changed, this became x1. Let's see. I really hate how this softwares tend to be so clunky. Alright, this became 2, this became 3, 2, and then this one all the way at the end, this became 2, and this is 3, and then I guess the last one became 3 as well. Alright, so moving on to the next one, and I guess, yeah, let's just leave it like that. x2, this one became x3, this one became x2, x2 minus 2k, let's see, this is x2, 2 times x3, and then this one is x4, multiply times x3, let's go all the way to the end, this is x3, this is x4, this is x4, there you go. I believe all the signs remain the same, so I don't see any issues so far. I will make sure to go over it just to again make sure that I didn't make any mistakes. This is what I think. This is as hard as it gets for this project. Just make sure you don't mess it up. And I have the tendency of doing that, so that's why I'm telling you to go over things. So T4, maybe I should stop talking while I do this. That could also help. T4, this will become TL, and okay, and that will become TL. So this is my, all right. So that should be it for the equations. Again, I have my function, my f nonlinear, and then for each of the point I is equal to 1, it will take this form. For I is equal to 2, it will take this form. I is equal to 3, this form, and finally I is equal to 4, it will take this form down here. And what I did is I replaced the function that I was given with this function, and whatever you see at T1, T2, T3, or T4, I put an x parenthesis 1, x parenthesis 2, x parenthesis 3, or x parenthesis 4. The T naught or the T sub 0 and the TL are actually constant. Those are your boundary conditions. So in this case, I represent them as T0 and TL respectively. Let's see. So what I'm gonna do right now is I'm gonna say define constants, and you want to define your constants, these constants that were given down here. We want to define them within our f nonlinear file, because remember, the only two inputs that we're passing when we call this function is the I, which represents which current function we're working with, and then the x, which is the initial guess vector. We're not passing any of these values, so we have to define them within the function. So I'm going to begin by defining k naught, which is going to be equal to 18. I will define my value a, which is equal to 0.425. Then I have t sub 0 or t naught 450. And then I have my temperature at the length, which is going to be 75. There you go. So this this right here will represent the constant values for a function, and then we have our function. So that should be it for this part. I'm going to jump into the Jacobian section, and what I'm going to make sure here is that my delta x it's equal to 10 to the negative 5. So I can just write 10 to the negative 5 like this. That is for my delta. That will be the only thing that I need to do in that section. And then I'm gonna finally jump into my Newton-Raphson. Now this is my main code. This is the one that I'm supposed to run. So what I'm gonna do is I like to begin every code by doing like a nice clean beginning. I'm not bringing in anything old from my previous run, so I like to start by typing clear CLC and close all. The last one is not as relevant in this case, but what clear does is it erases my variables in the workspace, so I can start fresh. CLC deletes all the different stuff in the command window, everything that I have in my command window here. If I type CLC, it erases everything, so I'm not dragging anything from before. When I look at my results, I'm looking at the correct results. And close all, it closes all my graphs and different figures that I open and things like that. So I like to start fresh. I'm not gonna focus into adding too many comments into different things, because I want to keep this video as short as possible. So I will define my initial guess. As I mentioned before, I like to define it as an array. So x3 is equal to number, x4 is equal to number, and I'm going to go ahead and copy the values that I'm giving here for my initial guess vector. If you're confused for why am I using x instead of t, as I mentioned before, the computer doesn't really care what you're using. I'm trying to stay consistent, trying to keep the same as I was given, so that there's not too much confusion at the moment of when we're calling this function. This function is asking for an x. It doesn't really matter what it is, but you know, I just want to keep it simple so it's not too confusing. Now this is the number of equations. The number of equations has changed. Instead of using 2 equations, we're using 4. and the number of iteration is going to be kept at 100. Now open a file to which print the right output. I'm actually going to get rid of this. I don't really care about creating a text file for writing stuff. It really depends on the goal of the project, but I don't think in any part of this project it mentions anything about creating a file, .txt file, so I wouldn't worry about that. uh, while I'm here, I'm gonna go ahead and change this. Set the convergence factor for both the iterative node and the residual. So if you go inside of this big for loop that we have in here, if you go down here, it says the residual. So I'm gonna change this to 10 to the negative 5, and the second one I will also change it to 10 to the negative 5. Wait, no, never mind. That will stay like that. This is kind of like a double boundary. So this, if the residual gets to lower than 10 to the negative 5, that means we're good enough to call it a day, terminate the iterative process. And this is in case the code blows up. If the residual gets too big, we get to a stopping point. So I'm gonna go ahead and do one of the extra steps. So the initial elements of the Jacobian, I want to displace my Jacobian. So I'm gonna go down here. This is where the Jacobian is defined. I will go up here before x alt, and I'm gonna say xprintf, and my two double quotes, I'm gonna say the Jacobian at the current iteration, and then I'm gonna do that, and then I'm gonna display J, which is my Jacobian, and then I'm just going to add a new line. So this should show the Jacobian at every single one of the iterations. So at the first iteration it will show it, then at the second one, and at the third one, and so forth. So this will take care of showing the elements of the Jacobian. The temperatures, those are pretty much given in the code I already have. I'm gonna delete this again because I'm not using any files. I'm not using any solution to file. I don't want to create any files. I want to keep this simple, but if you want to play with that, you're more than welcome to. And let's see the initial residual. I believe that is everything for the first part, so let's go and run it. So if I maximize this, if I go ahead and run it here, hopefully I won't get any errors. So there's some commands, I see some things, and then if I go to my command window, find under line 15. So I guess I forgot to erase something. There it is. More of that file stuff that I say I didn't want my code, but somehow it's able to sneak in. Let's run it again, and I think I see some results. Iteration number x2 out of bound, if not linear. Wonder what happened. So let's. Alright, so I ended up figuring out what the problem was. One of the things that I did that actually worked is that I rewrote this instead of an array. I just rewrote them with two dimensionals. I don't think that this is actually what the problem was, but still it's one of the things that I did, so feel free to change it if you're having the same issues I was having. Everything stayed the same. I put it right here. There's the Jacobian at the current iteration, display the Jacobian, and then just create a new line. Everything in here should stay the same, but I did go and change in f nonlinear. I was missing a semicolon after I declared the variable a, the constant a. So make sure you go over back and fix that. So now if I go into my f nonlinear, and I'm sorry, into my Newton-Raphson, and I run it, I save my file and run it, I can see by my workspace that I already got some values. So I'm gonna go into my command window, and here they are. So on my first iteration number 1, the Jacobian at the current iteration is this matrix. Again, don't forget Jacobian is a matrix that you calculate. You should know how to calculate it for the purposes of the exam. But here's the Jacobian matrix. Here's my residual norm and my current solutions for T1, T2, T3, and T4. Then my second iterations, this is the Jacobian, my residual norm, T1, T2, T3, T4, and then iteration number 3, iteration number 4, 5, and iteration number 6. This is the corresponding Jacobian. I can see that my residual norm is actually 10 to the negative 7, which is very good. and my current solution for T1, T2, and T3, T4 are displayed. So I will use this solution. This X represents my solution vector for the temperatures, and then this one is my corresponding residual vector for all the different iterations. So this were the residual norms that I had at all the iterations, and I can see that the last one got very close to zero, which is what we expect when we're solving this kind of numerical method problems. So the next step, what it will ask us to do next is that we will use the same values for the linear coefficient, but we will set the nonlinear coefficients to zero. So we're gonna go back to the f nonlinear function, and we're gonna set this a value equal to zero. Now there are two ways that you can do this. You can create you can create a new f nonlinear file and a new Jacobian file, and then just rerun it from the main script. Or for the purposes of the quizzes, for the purposes of the both of the quizzes, the answer sheet and the online quiz, the iClicker quiz, which I guess is no longer an iClicker, you can just set this a value equal to zero and keep everything the same, and just run the code again, and you will see the difference, how the number of iterations shortened and how our solution has changed, because we have basically linearized the problem at this point. But that way you can see how it changed, how it behaves different. But other than that should be it for the project. I believe we did everything that the project was asking for. So yeah, if you have any questions or any concerns, please send me an email or send me a message through Web Courses, and I hope this was helpful. As I mentioned in my previous announcement, I'm very open to any sort of feedback. So if you like these videos, like and subscribe. No, just kidding. Just let me know your thoughts on it, and I hope you find this helpful. All right, bye bye.